Welcome to Naradar Academy. In this video, we are going to discuss about singularities, types of singularities, and how to find residue at singular points. Okay, so let's start with the definition of singular point. A point A is called a singular point of f of z if the first condition is f of z is not analytic at that point. Okay, not analytic at that point, but it is analytic at some points of every neighborhood of A. Okay, that is the point where the function is not analytic is called a singular point. Along with that, what is the other condition we require? It should be analytic at some points of every neighborhood of A. Okay, already I have posted a video regarding analytic function. I have given the link in the description box. You go through that video. Okay, right. So this is the definition for singular point. Now the singular points are classified into two types. One is isolated and non-isolated singular point. Isolated singular point means, suppose if I take a singular point A, then in the neighborhood of A, there should not exist any other singular point. Okay, that is, first we take a singular point. Singular point means automatically the given function is not analytic. Okay, then for this A, you take a neighborhood. In that neighborhood, apart from A, at all other points, the function should be analytic. Okay, so that means in this neighborhood A is the only singular point, no other singular point should exist. Okay, that is, the neighborhood should contain no other singular points of f of z. That type of singular points are called isolated singular points. Okay, if in a neighborhood you have two or more singular points, they are called non-isolated singular points. Okay, we primarily deal with isolated singular points. This isolated singular point is again classified into three types. One is removable singularity, another one is pole, another one is essential singularity. Okay, these are the three types of isolated singularity. Now, how do we say whether it is removable or pole or essential? For identifying this type, the type of isolated singularity, we need the Lorentz series expansion. Again, Taylor's and Lorentz series expansion I have given in a video. I have given the link in the description box. If you want, you can go through that video also. Okay. So for classifying the singularity as removable or pole or essential, what you have to do is write the Lorentz series expansion for the function f of z. Okay, in that Lorentz series expansion means it will contain both positive and negative powers of z, right? If the Lorentz series expansion has no negative powers of z minus a, then that is called removable singularity. The negative powers terms are there, no? That part is called principal part. Okay, in that principal part, no terms are there. If it is so, it is called removable singularity, right? And then, if the Lorentz series expansion only finite number of negative powers, then it is called pole. On the other case, if the negative powers of z minus a in the Lorentz series expansion is infinite in number, then that kind of singularity is called essential singularity. So primarily, where do we concentrate? Take the Lorentz series expansion. Okay, when will you write the Lorentz series expansion? Only when you have singular points inside the neighborhood. In that case only we will have Lorentz series expansion, isn't it? There are two types of series expansion. One is Taylor series and Lorentz series. Taylor series is applicable when you don't have any singularity inside the neighborhood. But when you have a singularity inside the neighborhood, your series expansion is called Lorentz series. What is the difference between Taylor's and Lorentz series means? In Taylor series, you will have only positive powers of z minus a. Because there is no singular point, no, so only positive powers of z minus a will be there. Whereas in Lorentz series, you will have both positive and negative powers of z minus a. Because there you have singular points. Okay, so the part of the Lorentz series which contain negative powers is called the principal part. Okay, if that principal part contains no terms, it is called removable singularity. If that principal part contains only a finite number of terms, it is called a pole. If it contains infinite number of terms, it is called essential singularity. Okay, this is the definition for these types. Okay, then their characteristic is if a is a removable singularity, then limit z tends to a, f of z will become a finite value. Okay, if a is a pole, then limit z tends to a, f of z will become infinity. So these two are their characteristics for removable singularity and pole. Okay, and then we classify pole according to its order. What do you mean by order of a pole? So what is a pole? Pole means the principal part in the Lorentz series expansion has only finite number of terms, no, that is 1 by z minus a, 1 by z minus a the whole square plus 1 by z minus a the whole cube, etc. It will be having only finite powers, no. Look at the power of the highest term, that is called order of the pole. Okay, if my Lorentz series expansion only has up to 1 by z minus a the whole square, okay, no cubic terms are there, only up to the square term if I have, means it is called pole of order 2. If my Lorentz series expansion has only one negative power 1 by z minus a, then the pole is called simple pole. Okay, if it contains more than two powers, that is power 3, 4 or etc., they are called poles of higher order. Okay, only for order 1 we call it as simple pole, order 2 we call it as double pole or dipole. Okay, then let us do some problems based on these definitions. Determine and classify the singular points. F of z is equal to sine z by z. So for identifying the singular points, you have to equate the denominator to 0. Okay, what is the denominator here? Z. So equate the denominator to 0. Z equal to 0. So z equal to 0 is the only singular point. Why we are doing so? Because see, this is a quotient of two functions, no? The numerator is sine function, the denominator is polynomial of z. So individually if you take the terms, they are differentiable everywhere. Sine is also differentiable and z is also differentiable. But here you are having quotient, no? When you have quotient, the denominator should not be 0. If it is 0, the function is not defined there. That is why we find out the singular points by equating the denominator to 0. This is the procedure for all the problems. So for finding the singular point, equate the denominator to 0. So here z is the denominator, equate it to 0. So this is the only singular point. Okay, since this is the only singular point, there is no other singular points. That means this is an isolated singularity. That means if you take any neighborhood of 0, there will be no singular point. So that is called isolated singularity. Okay, right. This is isolated singularity, no? So first one is we identify the singularity, then we classify it as whether it is isolated or non-isolated. After committing that it is an isolated singularity. For isolated singularity, there are three types, no? Removable, pole and essential singularity. That type I have to identify. For identifying whether it's removable or pole or essential singularity, I am writing the expansion. Okay, f of z equal to 1 by z, keep 1 by z as it is, write the expansion for sin z. Sin z equal to z minus z cube by 3 factorial plus z power 5 by 5 factorial minus etc. Okay, now multiply this 1 by z inside. So you are getting like this, no? So here see, all are positive powers of z, isn't it? No negative terms are there. So there is a singular point but there is no negative power in the Lorentz series expansion. That means it's a removable singularity. Okay, also let us verify. Already I have given one characteristic for removable singularity, no? Limit z tends to 0, f of z equal to. See, this is f of z, finally we have arrived, no? Here you substitute limit z equal to 0. So 1 minus every other term will become 0. So only 1 we have. This is a finite number. So here also we can again confirm that this is a removable singularity. Okay, right. Then the next problem, f of z equal to cos z by z square. So for finding the singular points, equate the denominator to 0. So z square equal to 0, that means z equal to 0. So no other singular points are there. Again the same reason. Numerator is cos z and denominator is z square. Individually they are what? Differentiable function. Cosine is a differentiable function and z square is also a differentiable function. But you have quotient of these two functions here. So when the denominator is 0, the function is not defined. Okay, therefore when the denominator is 0, the function is not differentiable and hence it is not analytic. Therefore 0 is the only singular point. No other singular points are there. Therefore this will become an isolated singularity. So next I am going to identify whether it's a removable or pole or essential singularity. For that you write the expansion as in the previous case. 1 by z square into, for cos z it is 1 minus z square by 2 factorial plus z power 4 by 4 factorial minus etc. Multiply this 1 by z square inside. So 1 by z square minus this z square get cancelled. So 1 by 2 factorial plus z square by 4 factorial minus etc. Now look at this expression. Only one negative power of z is there. Remaining afterwards you are having only positive powers of z. So in the Lorentz series expansion you are having only one negative power, no? Okay, right? And it is of order 2. So z equal to 0 is a pole of order 2. If you simply have 1 by z alone, you say it is a pole of order 1. Okay, you should look at the degree of the highest negative power. Here the only one negative power is there and that is of degree 2. So z equal to 0 is a pole of order 2. Okay, right. Then for pole, limit z tends to 0, f of z is equal to, you substitute z equal to 0 here. See, 1 by 0 infinity, all the, even though all other terms become 0, infinity plus anything is equal to infinity only, no? So limit z tends to 0, f of z equal to infinity. So the characteristic for being a pole is also satisfied. Okay, then next problem. F of z equal to z minus 2 by z square into sine 1 by z minus 1. Now let us equate the denominator to 0. Here z square is the denominator. So equate it to 0. So what we get, z equal to 0 2 times. So z equal to 0 is a pole of order 2. Here I didn't write it as it is an isolated singularity. Here I didn't write it as after that I didn't verify its pole. See, whenever you have polynomials, you know, you will be definitely getting it as what? Isolated singularity only. Only for very rare cases you will get non-isolated singularity. So here itself I am writing z equal to 0 is a pole and it is of order 2. Okay, because no other terms are here, no? Right. Apart from this, you have one more term here, no? Sine of 1 by z minus 1. If you simply have sine z or cos z, no need to do anything with this factor. But here it is 1 by z minus 1 means what? It will come in the denominator, no? So some more singular points are here. Okay, here from this factor I have identified 0 is a singular point. Apart from this singular point, this function is having some more singular points from this factor, because it is what? Not sine z, this is sine 1 by z, my 1 by is there, no? So you have to expand this function for identifying the next singular point. So let us expand this. Z minus 2 by z square into sine z. What is the expansion? 1 by z minus 1 minus 1 by z minus 1 the whole cube by 3 factorial plus 1 by z minus 1 the whole power 5 by 5 factorial minus etc. Now look at this expansion. Already for this term I have written 0 is a pole. Now for this factor you look at this expansion. This is the Lorentz series expansion and z equal to 1. If you equate the denominator to 0, what will happen? Z equal to 1. Z equal to 1 is a singular point. But what kind of singular point is that? It is an essential singularity, because see, there are infinite number of negative powers. All z minus 1s are coming in the denominator, no? When it comes in the denominator, it is called negative power. That is called the principal part of the Lorentz series. The principal part of Lorentz series contain infinite number of z minus 1 terms. So this is an z equal to 1 is an essential singularity. Okay, then next problem, f of z equal to z minus sin z by z cube. Now equate the denominator to 0. So z cube equal to 0, that implies z equal to 0. Okay, but definitely it will be an isolated singularity, but directly I am not going to write it as a pole of order 3, because look at the numerator here, z minus sin z is there, no? Whenever you have trigonometric function or exponential function, okay, you have to check it again for the order of the pole, or whether it can be removable or it can be essential singularity. So for that, in order to identify the nature of this singular point, I am writing the expansion z minus sin z is z minus z cube by 3 plus z power 5 by 5 minus etc. no, divided by z cube. Now you subtract, z get cancelled. So what you have? 1 by z cube into z cube by 3 factorial minus z power 5 by 5 factorial plus etc. Multiply this 1 by z cube inside. So what I get? 1 by 3 factorial minus z square by 5 factorial plus etc. Right? So look at this term, no negative powers are there, isn't it? Therefore, z equal to 0 is a removable singularity. Can you understand? By equating the denominator, we identify 0 as a singular point, but here itself you cannot write it's a pole of order 3. You should not write it here because the numerator is something different, no? Is it minus sign is it? So I have expanded and I have checked what type of singularity is there. If you have any doubt about the order or type of singularity, you simply write the expansion. Then you can identify whether it is a pole or removable or essential singularity. Okay, right. Then next problem, f of z is equal to e power 1 minus minus 1 by z square. See, here you are having exponential function, but there is no denominator. Only you have to expand this function, and then from that expansion you have to identify the singular point and the nature of the singular point. So let me expand. Equal to 1 minus 1 by z square by 1 factorial plus 1 by z square the whole square by 2 factorial minus 1 by z square the whole cube by 3 factorial plus etc. By looking at this, you can easily say that all z squares is coming in the denominator, no? So 0. 0 is the singular point. And this expansion contains infinite number of negative powers, so it is an essential singularity. Okay, right. So 0 is a essential singularity. So that's all. Next one is, so we have completed the types of singular points. Now we are going to find the residue of a given function at the singular point. So what is a residue? So if A is an isolated singularity for f of z, then the residue of f of z at z equal to a is the coefficient of 1 by z minus a in the Lorentz series expansion. Okay, so if it is a singular point, means you can write Lorentz series expansion. In that Lorentz series expansion, look at the coefficient of 1 by z minus a. That is called residue. Okay. Other words, for Lorentz series expansion, you have a very big formula. No? From that formula, we can write residue of f of z equal to 1 by 2 pi a integral over c f of z dz. Right. Okay. So this is the formula. Only in very rare cases only we apply this definition. That is coefficient of 1 by z minus a. Okay. For simple problems, we have three different types of formula for calculating the residue at the poles. Okay. The first case is if A is a simple pole. If A is a simple pole of f of z, then residue of f of z at A is equal to limit z tends to a, z minus a into f of z. This is the formula when you have z equal to a is a simple pole. Okay. Then the second case is also for simple pole only. But in this case, suppose you have your f of z as quotient of two functions h by k. Okay, quotient of two functions h by k, where h of a is not equal to 0 and k of a equal to 0. In this case, while doing the problem, you can understand why do we have two different formula for simple poles. Okay. So in this particular case, the residue of f of z at a is given by h of a by k dash of a. Okay. So two different formulas you have for finding residue at a simple pole. Then, if you have a pole of order m, that is pole of higher orders, order 2, order 3, etc. In that case, residue of f of z at a is given by g m minus 1th order of a, where what is g means, that is this f of z is there, no? You write it as g by z minus a power m. This is the term containing the pole. Okay, you keep the term in the denominator, rest of the terms you take as g of z. Find the m minus 1th derivative. Here pole of order m, I said no. Okay, if it is of order m, find the derivative up to m minus 1. Okay, then substitute a there. So g m minus 1th derivative of a by m minus 1 factorial. So these are the three formulas for calculating residue of f of z at a given singular point. Now let us do some problems for finding the residues. The first problem, find the residue of f of z equal to z plus 1 by z square into z minus 2 at its poles. See, while doing the previous problems, for finding the singularity, we have equated the denominator to 0 and then we identified the nature of singularity by writing its Lorentz series. Okay, no need to go by that way every time. Okay, because in the initial stages, while for understanding the concept, you have to do in that way. Afterwards, no need to write. You see, look at the function given here. Numerator and denominators are polynomials in Z, no? So, whenever you have these types of problem, equate the denominator to 0, and whatever points you are getting there, that will automatically will become pole only, because numerator and denominators are polynomials only, no? So whatever singular point you are getting here, that will automatically will become pole, and whatever order you have here, that will become the order of the pole. So z square equal to 0 means z equal to 0 is a pole of order 2, and z minus 2 equal to 0 means z minus 2 equal to 0 implies z equal to 2. This is a pole of order 1. Okay, so two poles we have. One is simple pole, another one is pole of order 2. First, let me find the residue at the simple pole. Residue of f of z at z equal to 2. For simple pole, for what is the formula? Limit z tends to 2, z minus 2 into f of z. Okay, so limit z tends to 2, z minus 2 into what is f of z? Z plus 1 by z square into z minus 2. So this z minus 2 get cancelled. Simply what I have, limit z tends to 2, z plus 1 by z square. So 2 plus 1 by 4 equal to 3 by 4. So residue of f of z at z equal to 2 is 3 by 4. Next one, in the double pole, I am going to find the residue. 0 is a pole of order 2, no? So residue of f of z at z equal to 0 is equal to, what's the formula? If it's of order 2, g dash of 0 by 1 factorial. Now what is this g? G is nothing but part of f of z without containing the pole term. What is the pole here? 0, no? Which is the term containing 0 here? Z square. You leave that z square. All the remaining terms is your what? G of z. So g of z is z plus 1 by z minus 2. Right? Find g dash of z. First order derivative. This is of u by v form, no? So what is the differentiation? V into differentiation of u. So v is z minus 2 into differentiation of numerator is 1 minus u into differentiation of the denominator is 1 divided by v square, z minus 2 the whole square. So in this g dash of z, what you have to substitute? Z equal to 0. So substitute z equal to 0. What I am getting is minus 3 by 4. So g dash of 0 by 1 factorial. 1 factorial is 1 only. So minus 3 by 4 is the residue at the point 0. Okay, so at both the poles, I have founded the value of the residues. Right? Then the next problem, find the residue of f of z equal to tan z at z equal to pi by 2. See, for this problem, they are not asking you to find the singular points. They are asking you to find the residue at only at this point, pi by 2. Now f of z is what? Tan. Tan can be written as sin by cos. Okay. So when will this become 0? When the denominator is 0. Denominator cos z is 0 when z equal to pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2, etc. So all are poles. But only at pi by 2 they are asking you to find the residue. Okay. So this is a simple pole. For simple pole, already you have a formula z minus a into f of z. That is not applicable here, because when you have function which contains polynomials, there only you can apply that formula. When you have trigonometric functions like this, numerator and denominator, that formula cannot be applied. It is invalid here. That is, you cannot use it here. So I am taking the numerator as h and denominator as k. Okay. What is the formula for residue? H of a by k dash of a. What is h? H is sin z. Okay, so sin pi by 2 divided by what is k? Cos z. What is k dash? Minus sin z. So sin pi by 2 by minus sin pi by 2. So the answer is 1. So for simple pole, in the beginning itself I told you, no, for simple pole you have two different formulas for finding the residue. When it's a polynomial, the formula is limit z tends to a, z minus a into f of z. When it is like a fraction of trigonometric or exponential function like this, you have to make use of the formula h of a by k dash of a. Okay, then next problem, find the residue of f of z equal to 1 by z plus 1 the whole cube at its poles. Equate the denominator to 0. What do you get? Z plus 1 the whole cube equal to 0. That means z equal to minus 1 is a pole of order 3, because it is cubic power, no? Okay, right. So pole of order 3 means, what is the formula for residue? G double dash of minus 1 by 2 factorial. Since it is of order 3, here you have to write up to second derivative. What is G? This is the term containing the pole, no? Omit the term. Remaining is called G. So remaining only you have 1. So G of Z equal to 1. If you differentiate any constant, the value is 0. So residue is also equal to 0. Then the next problem, find the residue of f of z equal to z by z square plus 1. Equate the denominator to 0. Z square plus 1 equal to 0. So z square equal to minus 1. That implies z equal to plus or minus I. So plus I and minus I are simple poles. Okay, let us find the residues at these points. So residue at z equal to I equal to limit z tends to I, z minus I into f of z. So z minus I into z by z plus I into z minus I get cancelled. So I have z by z plus I. Now you apply the limit. Z equal to I means what? I by 2I. So the answer is 1 by 2. So at I the residue is 1 by 2. Similarly for minus I, the residue is limit z tends to minus I, z plus I into z by z plus I into z minus I. Z plus I terms get cancelled. Simply I have z by z minus I. Now you put z equal to minus I. So minus I by minus 2I equal to what? 1 by 2. So the residues are 1 plus 1 by 2 and minus 1 by 2. Okay. Then the next problem. Find the residue of f of z equal to 1 minus e power 2z by z power 4 at its poles. Okay, now by equating the denominator to 0, you will get the singular points. But here you see you have exponential function in the numerator, and that too it looks like 1 minus e power 2 is it, no? So when you have functions of this type, it is better to write the expansion. Then only you can get the real nature of the singular point. Okay, so let me write the expansion. 1 by z power 4 into 1 minus e power 2z is 1 plus 2z by 1 factorial plus 2z the whole square by 2 factorial plus etc. Now when you subtract this plus 1 minus 1 get cancelled. So simply minus 2z by 1 factorial minus 2z the whole square by 2 factorial etc. Throughout you can take one z outside, no? You take one z outside and cancel with this z. So it will be minus 1 by z cube into 2 by 1 factorial plus 2 square z by 2 factorial plus etc. So this is the series expansion. In the Lorentz series expansion, you have only one term containing negative powers. That means this is a pole. Z equal to 0 is a pole. And what is the order of this pole? 3. If you look at this question, here it is z power 4, no? If you equate it to 0, you will get 0 is a pole of order 4. It will give you wrong information. Okay. Whenever you have trigonometric or exponential function like this, you write the expansion, then only you can identify the clear nature of the singular point. Okay, when you have polynomials alone, no need to write it like that. Directly you can equate the denominator and write the nature of the pole. But when you have exponential or trigonometric function, it's better to write the expansion and identify. Otherwise you may get wrong. Right? Okay. Right. Now f of z I have written, no? So f of z equal to, let me write it again, minus 2 by 1 factorial z cube minus 2 square 1 by z square. That is, I am multiplying this 1 by z cube inside. So I am getting it like this. So hereafter no need to go for the formula. We can make use of the definition itself. What is the definition for residue? Coefficient of 1 by z, isn't it? Look at the 1 by z term here. This is the 1 by z term, no? What is its coefficient? Minus 2 cube by 3 factorial. So residue at z equal to 0 is equal to minus 2 cube by 3 factorial. The highest order you have to look for order of the pole. But for writing the residue, you have to look at the coefficient of 1 by z minus 0. Don't look at this term. This is for identifying the order only. Okay. For writing the residue, you have to look at the first order only. So minus 2 cube by 3 factorial. So minus 8 by 6, it is simply minus 4 by 3. Okay. Right. Then one more problem. Find the residue of f of z equal to 1 plus e power z by sin z plus z cos z at z equal to 0. Right. Now here this is also containing exponential and trigonometric function, but there is no subtraction here. It is simply 1 plus e power z. That e power z is also coming in the numerator. So no problem about the numerator. Okay, this will not give you any singular point. So for finding the singular point, we can equate the denominator to 0. So when will this become 0? When both are 0. That is sin 0 0 and z, when z is 0, this entire term will become 0. But they have given it clearly, only at 0 we have to find the residue. Right? Okay. 0 is a simple pole. For simple pole, what is the formula? H of a by k dash of a. Here h is the numerator, 1 plus e power z, and k is the denominator, sin z plus z cos z. Now let us find the derivative of k. Now differentiation of sin z is cos z, plus here z cos z product term, no? So you apply uv rule, z into minus sin z plus cos z into differentiation of z is 1. Okay, so what is the formula for residue? H of 0 by k dash of 0. So 1 plus e power 0 by 2 cos 0 minus 0 sin 0. E power 0 is 1. So 1 plus 1, 2 by 2. 2 by 2 equal to what? 1. So this is the residue of f of z at z equal to 0. Okay, I hope you all understand this video. Thank you.